We'll start recording today's lecture. Um, we are taking a break from the axioms of the real numbers. Today we're looking in section 2.2 in the textbook. And before we get to the actual material from 2.2, I want to do something, just remind you of something slightly different. And let's think about the plane, which would be R2, with what's called the Euclidean norm, and that's usually denoted with double bars. Okay, so let's take a vector in R2. What do we define it to be? The Euclidean norm of that vector is the square root of the squares, right? Okay. And what does this thing do in the plane? Well, it measures magnitude. Okay, that's how we tell how long a vector is. And there are several different norms we could use. This is just the most common one, is the Euclidean norm. So if we're in the plane, we got our vector v, then the Euclidean norm is that distance. Okay? Now, what are its properties? Okay, number one, this norm is equal to 0 if and only if our vector is equal to 0. Okay. Let me point out that that 0 and that 0 are different zeros. This one really means the origin. It means the 0 in the plane. Okay? So what I meant was not equal. The first one is the real 0. The second one is the vector 0. 2. If we multiply by a scalar, then that just scales the vector by the absolute value of the scalar. So this is for all a and r, those are real numbers, and vectors in the plane. And the third axiom, these are norm axioms, I guess that's the right word, is, does anyone remember the name of the third axiom this we usually put here?
The triangle inequality?
Yes, the triangle inequality. So, the norm of u plus v is at most the norm of u plus the norm of v for every pair of vectors. Okay? Hopefully you've all seen these before. You agree that they're true for the Euclidean norm. There's a lot of different norms we could put on the plane, and there's a lot of different functions that would satisfy all three of these. Okay, and this is why we call it a norm, and it's a measure of magnitude. Now, before we go on, since I'm sorry. I'm trying to figure out what order I want to do these things in. What I want to point out next is that the absolute value is a norm on the real numbers. because it satisfies those three properties. Okay, so here I'm thinking about the real numbers as a vector space over the real numbers. Before I was thinking about the plane as a vector space where the scalars were real. Now it's the real numbers of the vector space, but the scalars are still real. They're still the same scalars. Okay, let's just run through those properties real quick. The absolute value of a real number, let's call our real number x this time, is 0 if and only if x equals 0. It's true, right? 2. The absolute value of a times x is, now, if you read 2 carefully, it says we want an absolute value there and a norm here. Now, in our context, those are just both going to be absolute values because the absolute value is the norm. So it's the absolute value of a times the absolute value of x. And then we would say, I want to make a distinction here. For all scalars a and vectors x, even though a and x are both real numbers. Okay? And then 3. The absolute value of x plus y is equal to the absolute value, the absolute value of x plus the absolute value of y. Okay. We've seen these things before. I completely forgot. I meant to draw you the picture just to remind you of why 3 up here is called the triangle inequality. And just let's go back for a second and see why it's called the triangle inequality there. If we have a vector u and a vector v, then we take their sum, that's that vector. And the triangle inequality is saying that the length of the long side, well, it's the long side in this example, the length of that is at most the sum of the lengths of the other two sides. Okay, that's true in any triangle. What does it mean in this new context where we're talking about real numbers? Well, our picture of the triangle inequality is a pretty degenerate triangle, right? So if we're going to draw that, let me do that down here. Well, we'd be on the real number line. We'd have 0. There are cases now. Let's say x is there, and let's say y is out here. So y is a little bit better than x, bigger than x, not better. Then x plus y is out here. And I hope you can see we've got a triangle here. It's just a very degenerate triangle. Okay. Okay, so the name triangle inequality comes from what it does in the plane. And then this is just, if we simplify things, we make our vector space just the real numbers instead of the plane, this is what that triangle inequality becomes. Okay.
I have a quick question about the 3 properties.
Yeah.
For the Euclidean metric.
Mm-hmm.
So, just like, are we taking the Euclidean metric and then deriving these properties from it, or do we have these properties and we've chosen the Euclidean metric to meet them? Or is it kind of like we have the Euclidean metric, it has these properties, and then we decided those are good properties, so we pick things like that?
Yeah, precisely that.
Okay.
First we had the Euclidean metric. It has those 3 important properties, and then mathematicians said, well, those are the important properties. Let's call anything that satisfies that a norm. Anything that
Okay.
satisfies those three, we'll call it a norm. And then we find out we can make a lot of different norms.
Okay.
Okay.
I've also heard that the term metric used.
We're gonna get to that.
Metric.
Yep.
Okay.
We're gonna get to metric here. By the end, as long as we don't get too delayed, I think.
Okay.
Okay, so absolute value is a norm. Now, let me start. That's all your introduction to today's stuff. Let me start where the book starts. Okay? What is the absolute value? Okay? Let me just, before we go on, let me just make a note about this notation. The absolute value is a function, right? So absolute value is a function. And what does it do? It maps from real numbers to non-negative real numbers. Okay, I'll use that notation for non-negative real numbers. But now we get into the problem of notation. Notationally, absolute value does not look like a function. It's not f of this, okay? So just as a matter of notation, what we do to denote functions like that is we put a little dot right in the middle. And all we mean is that's where the independent variable is going to go in this function. It's going to go where the dot is. Okay? So this is literally just notation. And it's the notation that we have to use for functions that don't look like functions. Notationally, they don't look like functions. But absolute value is 100% just a function. Okay? So that was just a notational aside. Now we're back to the question, what is this absolute value? Okay, let's act really dumb. Let's say we only know what we've learned so far in the book. Well, what have we learned in the book? We've learned trichotomy. It's the trichotomy property. And it says, for every real number, precisely one thing holds. One of the following three things holds. Either your number is 0, or your number is positive. Now, in the book, they called it, in the book, they used the notation bold P for the positive reals. I'm going to use R plus because it's much more standard. Okay? Or the negative of A is a positive real. Okay? So how do we define the absolute value? Well, remember, if we talked about this with the order properties, if A is a positive real, that means that that means that A is greater than 0. And if minus A is a positive real, that means that A is less than 0. Okay? This all comes out of the definition of greater than and less than. Okay? Again, I'm just trying to show you how this all builds from the axioms as we built it up. This won't matter, but I hope you can see that this is how we're building these things up. And so what's our actual definition? And of course, it's the definition you know. The absolute value of A is, it's the non-negative one of those three that it could be. So it's A if A is positive, 0 if A is 0, and it's minus A if A is negative. Okay, and I hope you all knew that. Okay, so we've taken 20 minutes to build to that definition that you already knew. Okay. Now, go back to these properties that I claimed were true. We can now make those properties a theorem. Okay. From that definition we just gave, I think part 1 is pretty obvious. From that definition, the only way you're going to get 0 is if A is 0. Okay. I guess I've switched variable names here. Down there, I used an A. I probably would rather have an X there. Let me just fix that real quick. Okay, all better? Okay, the only way that the absolute value of X is going to be 0 is if X is 0. Okay, that was part 1. But now we come to part 2. Oops, don't want to do that either. Now we come to part 2. There's actually something to prove there. Okay. How would you prove it? Any suggestions?
We could do cases.
Yeah. That's basically the thing you have to keep in the back of your mind whenever you've got absolute value is, as a last resort, cases. And, sometimes it's the only thing you can do. I think it's the only thing you can do. So we'll call this a proposition for all A and, let's see how I stated it up here. We'll get it the same. A and X in R. We have that. Okay. So we're going to prove it. A priori, there are a lot of cases here, right? A could be positive, 0, or negative, and X could be positive, 0, or negative. So it's 3 possibilities for each, so you'd have 9 cases. Okay. We can make it a little bit easier by saying that if either of them is 0, then we're done. Okay. If either A equals 0 or X equals 0, then, AX equals 0. And, one of the things on the right-hand side is 0. So I'll just lump those together because I can't come up with a better way to say it, and just say then the absolute value of A times the absolute value of X is 0. So what? So the result holds. Okay, because both the left and the right will be equal to 0. Okay. Now, A and X, neither of them can be 0 for the rest of the cases, so now we're down to 4 more cases. And, I don't really see a way around it if we're going to write this proof, so let's do it. If a is greater than 0 and x is greater than 0, then, and what we're doing is we're just going to go up to this definition, and we're just going to plug stuff in and make sure that our equality holds, right? So then ax is greater than 0. So the absolute value of ax is equal to ax is equal to that. I guess, let's try and be a little bit more let me just show you. If we really want to show a bunch of steps, what would we say? We'd say oh, I'm starting to regret doing this already. Okay, if a is greater than 0 and x is greater than 0, then the absolute value of a is a, and the absolute value of x is x, and ax is greater than 0, so the absolute value of ax is equal to ax. So there you go. So what I did is I just added some more steps to the first proof. Okay. Why do we know that part? That if a is greater than 0 and x is greater than 0, then ax is greater than 0? Anybody? So there's 3 possible answers I would accept here. Answer 1 is, I think there's a theorem from the previous section that says precisely this, right? Answer 2 is more vaguely, I'm sure something like this was in the previous section. Or answer 3 would be, because we just know that if we multiply two positive reals, we get a positive real, right? Okay, I mean, that's the kind of thing where, yes, you could drill down to the axioms to get that, but we're not going to worry about that in this course, okay? Let's say we wanted to finish this proof, even though we're not going to right now. If a is greater than 0 and x is less than 0, let's do this one final case here. It'll be the final case for us, not the final case of the proof. Then what's true? The absolute value of a is a, and the absolute value of x is minus x. And ax would be less than 0. So the absolute value of ax would be negative ax. So we'd have that. Okay. And I hope you can see where this is going. If a is less than 0 and x is greater than 0, and then if a is less than 0 and x is less than 0. Okay.
sentence?
Sorry, go ahead.
I was just gonna comment about a less than 0 and x greater than 0. Like that has the same proof as a greater than 0 and x less than 0, correct?
Yeah, sure. And so you could appeal to commutativity there, right? Um, in these formulas, a and x have the same role, so you could, yes, you could subsume that case. But still, best case scenario, you're looking at a case where one of them is 0, a case where they're both positive, a case where they're different signs, and a case where they're both negative. So best case scenario, you've got it down to 4 cases.
Professor,
Yes.
I don't understand how the absolute value of x equals negative x.
That's when x is negative.
Okay.
So then that negative is making x positive.
Oh, right. Yep. I get it now.
When x is negative, negative x is positive. Yeah. Okay. Good. So that's that part. That was part A of theorem 2.2.2 in the book. So this was theorem 2.2.2.A. Okay. So I guess let me write it this way. We've got theorem 2.2.2 from the book. Part A was the above. Part B says that the square of the absolute value is equal to the square of the number for all real numbers A. Okay. Let's just think about a proof of this along the side. Why is this true? Well, it's true because a squared is non-negative for all A. Okay. We actually proved that last time, because I remember we proved it because we said that's not true for the complex numbers, so one of our axioms has to not hold for the complex numbers, and it turned out that the ordering was what didn't hold for the complex numbers. So what does that mean? That means that the absolute value of A squared is A squared. Okay? But we actually know from part A, from the one we just did, that the absolute value of A squared is also equal to the absolute value of A times the absolute value of A. Okay. Which is the absolute value of A quantity squared. And there we go. That's what we wanted to show. Okay. Obviously that's not a careful proof. You're not supposed to turn in things like that, but I hope it convinces you for now. Okay, part C is if C is a constant greater than or equal to 0, then it's a little bit of a weird one. Well, what does it mean? What would it mean for the absolute value of A to be at most C? Well, if you think about it on the real number line, that means A is between minus C and C. Okay. That's part C of this theorem in the book. And part D is that it is true that A is between, oops, put my negative sign in the wrong place. It is true that A is between minus its absolute value and its absolute value for all real numbers A. I mean, you could go farther. You could say that A is one of those two things. Okay? But it's actually, this inequality is helpful sometimes. Okay. Any questions about that?
Could you prove part D with the previous part C, just having the absolute value of A in place of C?
Yes, that's exactly how you prove part
Like
D.
similar.
Yeah. Okay. So I realize that I've the introduction took quite a while, and we've got a little bit to cover. So I'm gonna, well, I wasn't planning to prove any of that anyway. So we're not gonna prove that. We're not gonna prove the triangle inequality, although remember that's true, but we've already written it down. So let me skip to the following corollary. In the book, this is 224. It's a corollary of the triangle inequality. And it says that if A and B are real numbers, then okay, the absolute value of absolute value A minus absolute value B is at most the absolute value of A minus B. And C says the absolute value of A minus B is at most the absolute value of A plus the absolute value of B. Okay, and you can see another way this is commonly written is just one of these is a lower bound on the absolute value of the difference, and the other is the upper bound. Okay. These both have quite clever proofs from the triangle inequality. So we actually will prove this. Again, we're using the triangle inequality. Okay, so for part A, we have A is A minus B plus B. So the triangle inequality shows that the absolute value of A, which again is the absolute value of A minus B plus B, because they're the same thing. Now we can group it that way. It's less than or equal to the absolute value of A minus B plus the absolute value of B. Okay. So, what do we have? The absolute value of A minus the absolute value of B is at most the absolute value of A minus B. Okay. Now, that's not all we wanted to prove. In fact, that's we want to prove it with an absolute value around that thing. Okay. So, oops, I said around that thing. I highlighted the wrong thing. We want it with an absolute value around that thing. Okay. So we have one lower bound on the quantity, the absolute value of A minus B. Now, if you think about it, for it depends on A and B. This is either a decent lower bound or it's completely meaningless. Okay, depending on what A and B are, this thing might be negative, right? So we also have, now there's two ways to do this. You can repeat the proof with the roles of A and B reversed, or you can just say there's nothing special about A and B, I'll just switch them. Okay? So if we just switch the roles of A and B, okay, because there wasn't anything special about them. Oh. No, I'm sorry. I'm going to go the first way. I'm going to switch the roles of A and B. Because otherwise I have to do some different algebra. Okay. How do we want to do this? Oh, let's just use the triangle inequality right now. Okay, and what do we get? We bring that over here. That's less than or equal to the absolute value of B minus A. But now, the absolute value of B minus A is the same as the absolute value of A minus B. Okay, why is that true? Because we multiplied inside the absolute value by a minus 1. Okay, and you can go back, even just go back to the definition of absolute value. If you change the sign of what's inside, the absolute value doesn't change. Okay, so really what we've shown is that the absolute value of A minus B is greater than or equal to both that and that. Okay. Now, these two are negatives of each other. Okay. So, if you're greater than or equal to some number and also greater than or equal to its negative, well, those are the two possible values of its absolute value. So that means that you're greater than or equal to its absolute value. Okay. That's a proof of A. The proof of B is even, let's prove B real quick. B is immediate. The absolute value of A minus B, that is the absolute value of A plus a minus B. but the absolute value of minus b is b, the absolute value of b. So, yeah. Okay. Are there any questions on this?
Could you explain again the last step of
Of the proof of A?
absolute value around that whole quantity?
Yeah, this part.
Yes.
So there are two possible values of, the way I think about it at least, there are two possible values of this. This is either or it's negative. Okay. And you might say, or it's zero, but actually no, if it's zero, then both of these things are zero. Okay, so it's one of these two values. Well, we're greater than or equal to both of them. So we're covered. Okay, no matter which value it actually is, we're greater than or equal to it.
Okay.
Okay. In a textbook, there are a lot of great examples of solving inequalities involving absolute values. And I'll just say about those that yeah, it's just case analysis. Sometimes there are clever tricks. Sometimes you can pull off squaring both sides, but not usually. Usually it's just case analysis. They're slightly tricky. You should practice one, but we don't have time today to do one. Okay. So practice one, or else you might have to practice it on the quiz. So practice it on your own first. That would be my recommendation. Okay. Now we've talked about it several times, but we do have a real number line, which is where our real numbers live. So let's say that's x, and that's y over here. The distance between 2 points on the real number line, that distance is the absolute value of their difference. Okay? Now, in some sense, this is just kind of a definition of what distance is on the real number line. Okay, there's really nothing to prove here. I said earlier that we'd get to metrics. This is a metric on the real number line. Okay. In R2, your metric is the norm of the difference of the vectors. Okay. And that tells you how far two vectors are apart from each other. So that's one vector, that's another vector, that's their difference. So if that's u and v, then this vector is u minus v, and the magnitude of u minus v is the distance between u and v. Okay? So in fact, what we've done is, if you do the same thing we just did, you take the norm of a difference. What we've shown is that you can actually turn any norm into a metric. Okay? If these fancy words scare you, don't worry. We're not going to talk about them in this version of the course. But in the previous version of the course, we talked about these all the time for the first month, basically. We were working with abstract norm spaces and abstract metric spaces. Okay, but in this version of the course, all we're working with is the real numbers and the absolute value. Okay. There's something else in this section of the book that we're not going to get to today, which is epsilon neighborhoods. So I promise when that comes up again, we will, I'll remember that we haven't done it, and we'll do background on Absalom neighborhoods. Okay. So we've reached the end of the class. I'll turn the recording